Hello there. In this video, I'll be talking about the angle to position nodon, position to angle nodon, the various tricks that we could do with them, and how angle values work in GBG. So let's begin with the angle system of GBG. So here I have a simple setup where I have an input that I can increase and decrease, and it controls the angle of this line. You can see here in the purple, this is the standard angle of whatever input I input here. So the number system of angles in GBG is for the positives, it goes from 0 to positive 180. And for the negatives, it goes from 0 to negative 180. Now, that doesn't mean you can't use values outside that range. For example, here I'm using an input of 475, but as you can see, that angle is basically the same as positive 115. So intuitively, you can understand that is because one full rotation around a circle is basically 360 degrees. So 115 here plus one full rotation will still end up at 115. So 115 plus 360, 475. That's why these two values are basically the same. And it still holds no matter how many rotations you do. Like for example here, end up at 125 with an input of 15625. So that's basically just 125 plus several rotations of 360, so, which ends up with the same angle. And the same thing applies for negative numbers. So I'll just show you here. When we go to like negative 475, if we add 360 here, that's just negative 115. So that's why an input of negative 475 is exactly the same as an input of negative 115. So for any nodon that outputs angles, like the angle sensor, for example, it will always output an angle between negative 180 and 180. And as for the inputs, for nodons that expect an angle input, like the angle to position nodon here, for any input that it gets, it doesn't matter if it gets input or if you add 360 or subtract 360. So whatever output that this will give out, if you add 360 or subtract 360, it's going to be exactly the same as before. So that's one potential nodon shape if for some reason you have random 360s lying around. And note here, the nodons where this works are for the angle to position nodon, for all of the hinge connector nodons, so X, Y, and Z, it doesn't matter. 360s don't change the result. And also for the camera direction nodon, so both of its inputs also expect angular inputs. Now note that that only works for those three nodes specifically. So what if we have an input like say 490 and we want to figure out what this standardized angle is for whatever reason? Well, that's where the angle difference nodon comes in. So what the angle difference nodon does is it basically just converts any angle addition or subtraction that happens at its inputs and outputs the equivalent value in the standard range from negative 180 to 180. For example, here we just put a 14, that just comes out as 14 normally, but if I put something like 200, so 200 is over 180, well, 200 is basically the same as negative 160 here. So let me see here. Yeah, 200 should be negative 160. So if you need to get this angle between negative 180 to 180, just use an angle difference nodon. It's very cheap, just one nodon. And this is also very useful when you're doing math or other calculations that don't involve the angle to position nodon. So for example, the comparison nodon. So let's say we have an angle and we want to know when we subtract 90 from it, if the angle will be positive. So for example, here, negative 150, and let's subtract it with 90. So let's start with negative 150. Now, if we try to subtract 90 from there, well, we know that this is going to move 90 degrees up here. And if we do that, we'll see that the result will be something positive. But mathematically, you see here, negative 150 minus 90 would still be negative 240. So if we want to check if the angle is positive, well, this wouldn't really work. So this comparison just sees a negative 240, so it still outputs a 0. So in cases like these, we would need to use the angle difference nodon. So here I do the same operation here, but now with the angle difference nodon, since this goes below negative 180, it loops back to the correct value in our range from negative 180 to 180. Now we can get the correct output where it says that our angle, the difference between these two angles, is indeed greater than 0. And now for this next part, I'll just go into explaining how these two nodons work. So first, let's start with the angle to position nodon. Angle position nodon has one angle input, and then a horizontal position output and a vertical position output. So here I've already laid out how those three values interact with each other. For example, here, if I have an input of 33 in the angle, these will be the horizontal and vertical outputs. So in this diagram, I already showed you what those two values mean. So basically, if you have a line with a length of 1 and it is tilted at that specific angle, its horizontal distance and vertical distance will be these two values. So it basically gives us the lengths of the triangle that's formed by our line, or you could also look at it as the coordinates of our point here. So for example, here, the coordinates of this point is just 0.84 in the x and 0.54 in the y. Now, this function is incredibly important as it basically lets us figure out the length of basically any triangle that we want, as long as we know its distance and its angle. Now, the outputs of the angle to position nodon only gives us the horizontal and vertical outputs for a length of 1. However, if we want to calculate for angles larger than 1, it's very simple to do it. For example, here, if I increase the length, say like 1.49. So here, this is the input, and the outputs of the angle to position nodon are still here, the horizontal and vertical. So to get the horizontal and vertical coordinates of this line, you basically just need to take the outputs of the angle to position nodon and just multiply it with the distance of your line. So in this case, just take 0.35 and multiply that by 1.49. That gives us its horizontal distance, you see here, and multiply this to the vertical output, and we get 1.39, which is this. So that's basically how we use the angle to position nodon to figure out coordinates. Now let's talk about the position to angle nodon. So you can see here the position to angle nodon is basically just a mirror of the angle to position nodon. So it has two position inputs and one angle output. So it's basically the opposite of the angle to position nodon. Here, if we give it a horizontal input of 0.69 and a vertical input of 0.72, we will get an angle value output of 46. And that's true for any of these values. Now you'll be thinking, well, my horizontal input and vertical input isn't always between 0 and 1. What happens if the value is bigger? So unlike the angle to position nodon, which has outputs that are only restricted to these specific values, the position to angle nodon can take literally any input and it will just give you the correct angle regardless of how large a distance is. So for example, here, just pick a random point. Let's say an x of 2.22 and a y of 1.03. You can see here that that would result in a distance of 2.45, but that doesn't really matter. When we put those two values into the position to angle nodon, it'll just give us the angle here. So as you can imagine, for any specific angle output, there's basically an infinite number of combinations. And that's basically how the position to angle nodon works. Now, these two functions are incredibly important in literally any application that deals with angles, circles, directions, triangles, and many more. And in reality, these functions are known through different names that you're probably more familiar. So the horizontal position output of the angle to position nodon is also known as the cosine of an angle. And the vertical position output is known as the sine of the angle. And since we can get the sine and cosine from the angle to position nodon, we can take those two and divide them like this to get the tangent, since the tangent is defined as the sine divided by the cosine. So if you need to implement the tangent function in GBG, here's how you do it. Now take note that this tangent function is a little inaccurate when you get close to inputs close to 90 and negative 90. So if your input is somewhere near 90 or negative 90, the output of this function will be quite off simply because of the limitations of calculations in the number system that GBG uses. So be careful when you do that. Now as for the position to angle nodon, this implements a function known as arctan2, which is not strictly a mathematical function, is more of a function used in programming and is a special variant of the mathematical arctangent function. So for the strict definition of how the arctan2 function is implemented, here is a diagram. So the output of the arctan2 function depends on the position of your inputs. So here I've listed all of the cases. So imagine that this is the center here in the middle, and your input is a coordinate somewhere around here. So if your input is somewhere here, so basically if your horizontal input is positive, this function will give us the arctangent of input y over x. So that's how you can get an arctangent in GBG. Now, if your input is somewhere here, so basically if your x is negative and your y is positive, the output will be arctan y over x plus 180. If your x input is negative and your y input is also negative, then the output will be arctan y over x minus 180. Then if your input is exactly here on this line, it's going to be 90, and here is going to be negative 90. And for standard applications of the arctan2 function in most programming languages, an input of 0, 0 will actually give a error. But for GBG, we don't do that. So GBG, if both inputs are 0, it basically just gives an output of 0, which is a special case here in GBG. Now, if for some reason you want to implement the arctangent in GBG, so not the arctan2 function, but strictly the arctangent, regardless of what your inputs are, well, here is a simple way of implementing it if you need for any reason. So here I've just added an absolute value here so that the operation done by the position to angle nodon is always in this area. And then added this comparison and map to invert the y input accordingly, depending on the x input, so that the output will still be correct. So this is how you implement the arctangent if you want. Now let's go through a few interesting uses of these two nodons based on their behavior. So here I'll just increase the input constantly, and let's watch the horizontal and vertical outputs of the angle to position nodon. See here, it does something interesting. It goes back and forth between -1 and 1, and it does it in a very smooth manner. So we can make use of this to make smooth movement or smoothing functions in GBG. So let me show you here. So normally if we want something to go back and forth, you could use something like a counter, for example, set to bounce. And if we just keep increasing it, we will see that this will just move back and forth, and when it hits the edge, it just bounces back immediately. Now, if we don't like that, we can use the angle to position nodon to replicate the same movement that we had here, which is much smoother. See here, thanks to the angle to position nodon where we map the outputs of the angle to position nodon to 0 to 1, you can make this movement, which is much smoother. So instead of immediately bouncing from one side to the next, here you can see that it gradually slows down whenever it reaches the edge, and it does this very smooth, fine motion. This is also not just limited to back and forth motions. We could also implement this in like just one directional movements. So for example, here, we're just moving this block from this side to this side. So you can see here, it just moves from left to right at a constant speed. Not so interesting. But thanks to the angle to position nodon, if we map it from, let's say, 90 to 0 for the horizontal. So if we recall, if this is If you take a look here at 90, the horizontal output as is at 0, then we slowly make it move to 0. You can see that its x slowly approaches from 0 to 1. So we can make use of that behavior, and instead of making our block move at constant speed, we can make it do something like this, where it starts fast and gradually slows down as it reaches the edge. So another interesting property of these two nodons that we can use is the fact that these two nodons are basically just mirrors of each other. So for example, if I take 0.81 and 0.59 and send it to the position to angle nodon, that's going to give me 36. And if I put 36 into the angle to position nodon, it's going to give me literally the same values. However, remember that the angle to position nodon only outputs values within this circle. However, the position to angle nodon can take literally any value that we want. Now this is interesting because you can imagine if we take, say, a random position here with the position to angle nodon and send it to the angle to position nodon, what's going to happen is it's just going to give us this value instead. So our input is this, but it gives us this value, which is basically the value of our input if the distance was 1. And if we try to sweep around here, you can see that basically if we have this system where we have the position to angle nodon connected to an angle to position nodon, we're basically converting any position here and basically normalizing it to this circle specifically. So regardless of how big or how far our distance is, it normalizes the magnitude of our value to just this one circle. So regardless of how far or how close our input is, we'll know that the distance is always the same. Now, where would this be important? So here, I'll show you a common example. Here I just have a setup where it shows you in which direction your stick is pointing. So here, you can see here, I'm just moving my stick around in a circle, or all around like that. You can see here, it moves around in a circle. Over here, I have a different input method. So instead of using sticks, I'm using buttons. Now observe what happens instead. So when I move the cardinal directions, it's basically the same as the stick. But when I move diagonally, you can see that the value, or basically the distance here, is at the corner there, whereas with the stick, it's over there. And if you can imagine, what's actually happening here is, instead of my input, so let's say this is my input to a person nodon, instead of my input being like diagonally straight like that, which is a constant speed of 1, what's happening instead is since I'm sending 1 horizontally and 1 vertically, what I'm actually sending to the person nodon would be around 40% greater than the original. So with that type of setup, moving diagonally would actually make me move 40% faster than if I were just moving in one direction. And this is different if I were using a stick nodon input system. Actually, this is a reason why if you've seen some speedruns of some older games, you'll notice that people will be moving diagonally for some reason. And that's because those games don't take this into account. They don't normalize their inputs, so when the player holds both forward and a direction, they're able to move much faster than intended because the value is not normalized. Now with these two nodons, we can fix that problem. So here I just took this original setup here that does that. And now when we put that into our system here, you see that when we try to move diagonally, it now puts the position at the correct place. So instead of moving 40% faster, now regardless of how many buttons or which direction I choose, my personal nodon will always be moving at the same speed. Another interesting property of these nodons is that, for example, if we start at an input 0, the vertical value is 0. And if we just increase the input in one direction, you'll see that the vertical output goes up, goes down, and goes back to 0. You see here, by just increasing the input in one direction, we went from 0 all the way back to 0. Now that property lets us do something very useful when we combine these nodons with a map nodon. So let's take this map nodon, and let me just reset this first. Set the input to 0 to 1, then send the output range to 0 to 180, and turn on range restriction. So now let's try to imagine what will happen with the output of this angle to position nodon, specifically the vertical position. So now let's imagine that the input to our map is 0. So with the map, we know that if the input is 0, the output will be 0, as you can see here. Now, if we set any value less than 0, well, since the range restriction is enabled, like for example here, -8 is less than 0, so it's outside this range, it basically just gets capped back to 0. So here, it will still output 0, and we know that any value that's less than 0 will still output 0. Now let's set the value to 1. So the maximum of our range here is 1. So we know that if the input is 1, the output is going to be 180. But we know that if the input to the angle to position is 180, its vertical output will still be 0. And the same thing if we put any value larger than this, so example 9. 9 is greater than this range, but since the range restriction is on, the output of the map will still be 180. So the output of this nodon will still be 0. Now with this setup, we've essentially made it such that if the input to the map is any number less than 0 or greater than 0, the output is going to be 0. So if you think about it, we've made this system where if the input is any number that's less than or equal to 0 or greater than or equal to 1, the output will always be 0. However, when the input is in between 0 and 1, the output is going to be non-zero, and we'll be able to activate logical nodons such as texture nodons, for example, which only check if the input is 0 or non-zero. And since we're using a map here, we can essentially set this map range to anything we want. So for example here, with these settings, if the input is in between -46 and 66, that will turn on this texture, but any value outside this range will not turn on this texture. So in essence, we've basically been able to replicate this system here, which checks if a number is between two numbers. For example, here, this is how you would typically check if a number is between -5 and 10. So if the number is between -5 and 10, only then will this AND turn on and activate this output. But using this special fact of the angle to position nodon, we're able to replicate the same setup that uses 5 nodons using only 2 nodons. And this is not just exclusive to the angle to position vertical output. For example, we can do the same thing for the horizontal position. So we know that the horizontal position is 0 when the angle is 90, and also when the angle is -90. So if we set the map from -90 to 90, we'll essentially have the same bounds here. So here, set to -90 to 90. And this will do the same thing as before, where if the input is less than here or greater than here, it's gonna send -90 or 90 to the angle position and therefore make the horizontal output 0. And any value in between these will be some value in between this, and output a non-zero value and activate logical nodons. The same thing for the angle difference nodon. So the angle difference nodon just calculates this specific standard angle. And we know that if we start at 0, it's going to be 0. And if we do one full rotation, or basically 360, it's going to go back to 0. So here I just set it to the range that we want and the output to 0 to 360. So when it's 10 or greater, the output is going to be 360, which if we send it to the angle difference nodon will still be 0. So we can actually use any of these three nodons to implement a range comparison between two numbers. Now, it doesn't really matter which one you use between these three. There's barely any difference between them, but if I had to choose, I would recommend using this one because the angle to position nodons are a little bit inaccurate. So when, for example, if we send a 180 here, the output here isn't exactly 0. It's actually going to be like 0.0000007 or something. So it'll still not activate textures, but yeah, if you strictly need a value exactly 0, I would recommend the angle difference instead, since that's a bit more accurate. Now, if you watch my additive logic video, this would sound familiar. Because in that video, I also showed a setup where you can do a range comparison using a map set to bounds of negative 0.0001 and 0.00001 followed by a knot. So these two nodons replicate this same setup where it checks if a number is between negative 5 and 10. So is there any reason or any difference between this setup and this bottom setup? So actually, if you pay close attention to these two setups, there's actually a very slight difference. See here. So in this angle setup, it actually excludes specifically the ranges that we set. So for example, if our input here is negative 5, the output will still not activate. If it's negative 5 or less, it's not going to activate, but only if it's strictly within negative 5 and 10, only then will it activate. However, on the other hand, with our map setup here, if our number is exactly the same as the range that we set, it will still turn on. For example, if you're checking if a number is strictly greater than or equal to negative 5 or less than or equal to 10, you can use this setup. However, if you want to check the same range but exclude negative 5 and 10, you should use this setup instead. So that's the only difference between these two. However, if it doesn't really matter to you, I would be more inclined to recommend this one because this one has a knot at the output and the output is always either 0 or 1. Instead of here, which you can't really predict what the value is. Now for this next section, I'll be discussing various shaves that we can do with the angle to position nodon and the position to angle nodon. So let's say we have an angle to position nodon and we want to get the position of an angle plus 90 degrees. To do that, we can just add a cosine 90 here. But the more efficient way to do this is actually, we can just take the same angle to position nodon and just use the vertical position output instead. So here we're effectively able to shave one constant nodon by just changing the output that we're using. And this works because the horizontal output of the angle to position nodon is related to the vertical position output. And here I'll show you. For example, here our angle is 23. And this forms this certain triangle with sides 0.39 and 0.92. Now, if we add 90 degrees to that, so basically if we rotate this triangle by 90 degrees, we'll end up here at 113. And here we'll basically have the same values as before. We have 0.4 and 0.92. But now instead of the 0.92 being the x-axis, now the 0.92 is rotated 90 degrees, and it's now the y-axis. So that's why if we have a certain angle and we look at the horizontal output, if we add 90 degrees, the vertical output value will now be basically the same as the horizontal output value from the original. And you can also take the same concept backwards. So for example, here our vertical output is 0.91. So we know that if we subtract our angle by 90, then we would know that this 0.92 here, when we rotate it by 90 degrees, will now be the x-axis. So in terms of nodons, that's reflected here. So if we have a vertical position output, if we want the vertical position output of an angle minus 90 degrees, so instead of subtracting 90 degrees to our input here, we can just simply change the output to the horizontal position output and save one constant nodon. Now this next shape has to do with the situation where, say we're using a angle to position nodon, and we want to get the inverted value of either its horizontal position, vertical position, or both at the same time. Well, here we can make use of the identity where we can just add a constant 180 here. So let me show you that here. So let's take, for example, angle 30. So angle 30 has horizontal output 0.87 and vertical output 0.50. Now let's imagine adding 180 to that. So if we add 180 to that, that's basically just rotating halfway across the circle. So that will be here at negative 160. And as you see here, since we're at the opposite point of where we were before, the horizontal and vertical values, their magnitudes, are still basically the same as before. It's still, there you go. It's still negative, it's still 0.5 and 0.86. But now since we're pointing it at the opposite side of the circle, we're basically just inverting the horizontal and vertical outputs. So that's why whenever we have a input to our angle to position nodon, if we add 180 to that angular input, whatever outputs that this original input would have given us will just be inverted, but the same value. So instead of using an extra inversion nodon or two inversion nodons to get these outputs, we can just simply add this constant here, which is pretty easy to shave later, to reach the same result. Now, what if we only want to invert one output? So for example, the vertical position. So we want the horizontal position output to still be the same, but we want to invert the vertical position. So here we can't really use our previous example here where we added the 180 because that would invert both of our values. So what we can do here instead is to invert the angle going into the angle to position nodon. And doing that is basically the same as inverting the vertical position output of our angle to position nodon. So let me show you how that works in our demo setup here. So let's say our input is 22 degrees. If we get the inverse of that angle, so negative 22, that's basically just this same angle, this same triangle, but on the other side here. So we're basically just reflecting our angle across this x-axis here. So the x value of our angle is still the same. So 0.92 here, 0.92 here. And what we're only changing here is the y position. So the magnitude of the y is still the same. We're just changing it from positive to negative and vice versa. And that's why if we want to change just the vertical position output, we can just add an inverter nodon at the input here instead. So now if you're looking at this in the vacuum, you might imagine, well, this doesn't really shave me nodons. But sometimes this matters in cases where you have other nodons that can shave this invert nodon instead. So for example, we're in a situation where this input is actually coming from a map. Now, since it's coming from a map, well, here we're using 3 nodons in total. But in this situation, since we're coming from a map, well, since the map is connected to the inverter, we can actually shave this inverter using this map by just simply changing this setting. And we can also do the opposite thing where, let's say, we have a map here connected to this output. So instead of using this setup, we can convert this setup to this setup, where we can shave this inverter nodon instead using the map that's connected to this output. Now note that this only works for the vertical position specifically. If we want to invert only the horizontal position, we need to do something else. And if you look here, it's basically the combination of these two systems. So here, to only invert the horizontal position and not the vertical position, what we can do is invert the input and then add a 180. So to show how that happens visually, let's go here again. For example, we take the angle 21 here. So if we invert it, it goes down to negative 21. And then if we add 180, we do a full rotation to the other side and end up here. So basically now, from our original angle here, we basically just mirrored it across the y-axis here. So that's why the y position in this case now stays the same. And now the only thing that changes is the x position, which has the same magnitude but different signs. So it goes from positive to negative, but the y position is exactly the same and the x magnitude is still the same. Now moving on to the position to angle nodon. Here, for example, if we want to take the position to angle nodon and invert the angle, well, what we can do instead is invert the vertical position here. So this is basically the mirror of what we did here, where we inverted the vertical position output and instead inverted the angle. And it's the same reason why this works. So just show you here, given the specific position and angle of 0.37 and 0.93, if we give the same horizontal input of 0.93 and give negative 0.37 instead, it's just going to get flipped here, and we're going to get the negative of the original angle. Then for this next one, let's say we have our position to angle here and we want to add 180, or basically flip our angle around 180 degrees across the circle. To that, we can do instead is add both of these inversions and invert both of our inputs here. And then lastly, if we want to invert and add 180 to our angle output here, we can just instead invert the horizontal input of the position to angle nodon, or vice versa. If we have an inversion here and we want to get rid of it, we can just change from here to here and potentially save these two nodons if we have a map or some other nodon that can do addition and inversion at the output. Now, one last trick that we can do with the position to angle nodon is flipping the inputs. So if we have this original settings and this original output, if we flip these inputs like this, that's essentially the same as inverting our original output and then adding a 90 here. So if you want to do this, you could just flip the inputs instead. Another way that you can look at this is by doing this instead. So this is basically the same thing as here, but I just subtracted 90 from both cases. So here, this is an alternate way of inverting the angle output of the position to angle nodon. So instead of doing what we had here, what we can also do is flip the inputs and then subtracting 90 from the output. That's essentially the same as getting the inverse of the original output. So one last important thing I need to tell you about these shapes with the position of the angle nodon is that if we're adding an angle directly to the output here, keep in mind that this doesn't work if both of your inputs are 0. So this is because in the real world, if both of the inputs to this function is 0, that's supposed to give us an error. So the result no longer makes sense. But here in GBG, if both of the inputs are 0, that gives us 0, which gives us this weird case where the answer becomes incorrect. So just keep that in mind if you're going to use any of these shaves. That's basically all of the basic shaves that we can do with the angle to position nodons and position to angle nodons, which might be useful for you if you're used to playing around with them or doing a lot of math with them and want to shave a few more nodons. So that's all for this video, and thanks for watching. See you in the next one.